All right, welcome to day number 7 of C and Software Tools class. Today we're supposed to be talking about arrays, a topic you're familiar with from Java. It's just taken us a couple of days to get here, learning a new language and some of the tools along the way, but we'll get through as much as we can today about how arrays work in C and some ways that they're different from what you're accustomed to from Java. You can see there's a lot of stuff we hope to do, starting with the basic array syntax and working our way to passing around multi-dimensional arrays between functions before we're done. When you make an array, you know how arrays work. An array is a bunch of elements all with the same type. And when you declare a new variable that's going to hold an array, that's the stuff that you have to say, just like you do in Java, although you say it in different places in C. If you want to make an array, here's a syntax for how to, or here's an example of the syntax for making a new array. So just like Java, the type goes out front. You're making an array where every element is this type. Every element is an integer. But then in Java, you can put the square brackets right after the type in the array. In C, the square brackets go after the name. So after the type comes the name of the array, and then inside square brackets, the size for the array. And then like any other variable declaration, a semicolon to mark the end of the declaration. So this is a weird part of C compared to Java. It's something that they probably wish they had done differently now, but it seemed to make sense when they were first defining the language, and that is that the type of this array is kind of in two places, or the type of this variable is in two places. For an array, part of the type, the name of the, or the type of the elements is out here in front, and then the fact that it's an array and how big it is out here after the name. And that may not seem like a big deal, but once you start composing things, when you start making an array of other stuff, this can get a little bit tricky. We'll still learn how to make sense of it. We'll learn how to read and write types, but it'll be a little trickier than it was in Java because some of the typing information is on either side. In some places, arrays are required to have a size that's a constant expression. So this 10 here, in some places, has to be a constant expression. And when I say in some places, I mean, depending upon where you put that array. And we'll see one example today. If you can make arrays as local variables in a function, and there that doesn't have to be a constant expression. But if you make a global array, if you declare an array outside any function, then it does have to be a constant expression. I'll say that again later, and as we introduce new places you could put an array, I'll let you know whether it has to be a constant expression or not there. So here's how you make a new array. Unlike Java, declaring the variable makes the array. You remember from Java, when you make an array, you're making a reference, and then you have to use the new operator to actually allocate an array for it to refer to. Not so in C. When you declare a variable like this array A here, you've got a 10-element array. It gets made just by the declaration. So this is all you need to make an array with space for 10 integers. Once you make an array, how do you use it? Well, fortunately, the syntax here is what you're familiar with. If you've got an array like the one we just made and you want to access one of its elements, name of the array A, and then the index of the element inside square brackets, just like it is in Java. And just like Java, in fact, just like most programming languages, the indices go from 0 to n-1, or I guess said better, if it's an n-element array, then you've got n elements. They're just indexed from 0 up to n-1. As a little aside, and I invite you to never do this, but you can write the name and the index backward on an array in C. The array name, normally we do what I've got at the top. Everybody does it this way, but it also works if you put the index here and then the name of the array in square brackets. And there are a few people who like to do array syntax like that. I don't think this is really an accommodation to those few people, but we'll see later why that works once we understand what's really going on when you work with an array. For now, we'll just say this is a weird thing that works that you probably don't want to do because most people, even if they know you can do it, they're not accustomed to this. So we won't use this feature except maybe just to show off. This is how we'll index into an array with the name of the array first and then the index inside square brackets. I think I already said this a slide ago. When you declare a variable, you're making the array. Whereas, and I've said this, whereas in Java, it takes a separate expression to allocate space for the array. I'll go ahead and say arrays can be allocated on the stack, like local variables. They can be allocated statically, like global variables, or they can be declared as either of those types of variables. So where you declare the array, or really where you put the declaration in your code, determines its storage class, just like any other variable. Whereas in Java, arrays are always allocated using the new operator, which means they're always allocated on the heap, or at least if we were talking like a C programmer, that's how we describe how they're allocated. We haven't learned how to do that in C yet, but we will be learning that soon. I guess the point I want to make is in C, you get more choice for how that array should be stored. Questions before we move on? The place you declare it determines how it's initialized, just like any other variable. So if you allocate an array on the stack, if you allocate it like a local variable, and you don't put anything in it, then it's going to start out probably containing garbage. Like any other stack variable, it starts out using the same memory that you've probably used to store other stack variables before you started using that memory for an array. So this sample code up at the top, if you make an array A with room for 20 elements, but I didn't put anything in it and I just started printing out those elements, at least when I ran this sample program, that's the garbage I got when I printed it out because I was just using uninitialized stack memory. If you statically allocate an array, like if you make it a global variable or a static local variable, then it behaves just like any other statically allocated variable. If you don't initialize it, it starts out full of zeros. If you want to put something in it, how can you do that? Well, you can do it the slow way, or I guess since we already know how to access array elements, you could just go through each element individually and put something in there. If you made an array A with room for 20 elements, you could put a 7 in element number 0, 14 in the element at index 1, and so on. And that's fine. That's normally how you put stuff in an array element and how you use the same syntax for looking at what's in that element. But when you make a new array, there is a special initialization syntax that makes it easier to put stuff in there all at once when you make it. And this is called array initialization, or the initialization syntax for an array. I think it's very Java-like. The way it works is it starts out looking just like an array declaration, but instead of a semicolon at the end of it, you put an equal sign and then inside curly brackets, the sequence of values you want to put in that array. So here I'm making a 5-element array. I'm telling the compiler, I want 7 to go in element 0, 14 to go in element 1, and so on. I was careful to make sure that the number of initialization values I gave matched the size of the array. So I said I wanted a 5-element array, and I gave exactly 5 elements. If you give fewer elements at initialization, that's called partial initialization, and that's okay. You can, like in this next example, I ask for a 5-element array, but then I only initialize 3 of its elements. That's okay. You can initialize fewer elements than you have. And again, that's called partial initialization. And if you do that, all the elements you don't explicitly initialize automatically get initialized to 0. Even if the array is a stack allocated array. Remember a slide or two ago, I was trying to make the point that for a local variable that's an array, for a stack allocated array, if you don't initialize its elements, or if you don't initialize it at all, it starts out full of garbage, whatever was there on the stack. But if you partially initialize it, anything you don't explicitly initialize gets set to 0. So it's kind of all or nothing on that. A couple of other tricks you can do with the initialization syntax. If you're going to initialize the array with a sequence of values, then you can let the compiler figure out how big the array is based on the number of values you give. Here at the top, I'm giving 5 values in the initialization expression, but I didn't say how big the array was. That's okay in C. The compiler will say, oh, you must have meant 5 here because you gave 5 initialization values. And I'll go ahead and say, it's okay to do that on the outermost index of a multi-dimensional array. We haven't seen those yet, but just as a warning, you can do this, but if you have a multi-dimensional array, you can't do this on every dimension. We're only looking at one-dimensional arrays here, so there's only one dimension. So in the case of a one-dimensional array, you can let the compiler figure out how many elements it has based on the number of elements you give. If you're doing initialization, at least the older syntax, you had to do the initialization from the start of the array, one element after another. C99 introduced a syntax that lets you jump around the array if you want, or even skip over elements. And I'm showing that at the bottom of this slide. So the C99 standard lets you put an index inside square brackets, and then equals, and then a value you want that element to get. And this example says, I want element 7 to get a value of 10. So that's where this 10 came from out here. That's at index 7. You don't even have to do them in order. It probably makes sense to do them in order, but just to show off what you can do, I deliberately jumped around here. So after I fill in element 7, I go back and say element 2 needs to have a 40 in it. That's where this 40 came from, and element 5 needs to have a 35. That's where the 35 came from. The size of the array, notice I didn't specify that. And just like above, the compiler will infer the size based on the index, the biggest index you give. So I gave 7 as the largest index that I said anything about. So the compiler is going to assume I want an 8-element array. Since if I've got an index 7, I must have at least 8 elements. You can even mix the syntax. The older syntax just lets you list values one after another. The new syntax lets you, the C99 syntax lets you explicitly say, put this at index 7, put this at index 2. What does it mean to mix them? Well, if you give a value without explicitly saying where it goes, it just goes right after the previous value you specified. If you give a value and there's no previous value, it just starts from 0. So think of, if you don't give an index, it just continues from where it was. So this, in this example, this 1 goes in the first element, goes in element 0, because there's no previous element. So that's just like the older syntax. And then I jump over to 7 and say, put a 10 there. So that's where this 10 comes from. And then I didn't say anything about it, but this 90 comes after it, because like I said a moment ago, if you don't say otherwise, it just continues with the previous, continues right after the index of the previous value. And then I go back to element 2 and I put a 40 there. And then I put a 2 after that because I didn't say otherwise. And then I jump over to element 5 or index 5 to put a 35. So we've seen arrays, we've seen an array initialization, and we've seen partial initialization using both the older and newer syntax. Questions?
I have a question.
Sure.
So if you were to just put more numbers after, for example, the 5, like 2 more, would it override what you had in 7?
It will. I think this is a good question. It's a common question. I should get better at answering it. But you're saying, what if you said after this 35, you said 40 and then 50? Well, the 50 would kind of overwrite this 10. I know the first time someone asked me that, I said, yeah, I think you can do that, but I sure wish the compiler would warn me about that. And I tried it and I didn't get a compiler warning about that. My memory of what I got was whatever the last value you specify for an index is, that's what's going to end up in the array. Whether or not you get a warning would be a compiler choice. And I'd
Mhm.
like my compiler to warn me about that because there's really no point double initializing a value. But at least GCC didn't warn me at the time.
Okay, thank you.
Yeah. I would say, even though that can work, why would you want to do that in your code? It just seems like it would be confusing and maybe, harder for people to maintain if you've got this double initialization of a value. But I think you can do it. All right. This is one of the first potential mistakes, big potential mistakes we're going to see. And that is in C, arrays are not bounds checked. In Java, if you make an array and then you accidentally index off the end of an array, like if you make an array here with 6 elements, so it's got element 0 up to element 5, and you accidentally try to get element 7 or even element 6, the Java runtime environment throws an exception when you try to do that, which means every time you try to look up something in an array, it's paying a little bit of extra work to check and make sure you're giving it a legal index. In C, you're not guaranteed that. In fact, the C execution environment doesn't check that for you, which means if you think of your array, it's stored somewhere in memory. Like I make an array of 6 zeros here. You can do this trick. This is, well, the standard doesn't seem to say that you can do it, but the GCC compiler lets you do this. So we're going to pretend it's okay this semester. And that is, I did partial initialization and I didn't put any values there. But because it's still partial initialization, I get an array full of zeros in that case. Well, that's a bunch of zeros stored in memory one after another. Well, in that memory, my program is probably storing some stuff after where that array is stored and before where that array is stored. And if you index off the end of the array, if you do an out of bounds index on the array, you're actually going to be accessing the memory for whatever's stored after the array or whatever's stored before the array in memory, because all your variables are stored in memory to an extent, just packed together one thing after another in memory. So an out of bounds index would let you accidentally access stuff that maybe you didn't mean to. Here's an example program that shows that this really happens. So here I ran this on the Common platform. It's been a couple of years since I've tried this out, so you might see slightly different behavior, but it shows the point I was talking about. I make an array A here with 3 elements, and I stick a variable right before and right after it. And then I print out these 3 elements playing nice with the system. And sure enough, I get 10, 20, 30, just like I put in the array. And then I start looking at what's before the array in memory. I back up to an index of -1. So I'm trying to access an element before the array even starts. And I get a 50. Now the standard doesn't promise this, but I bet that's my variable y right there. Even though I declared it after the array, I bet it's actually stored in, looking at it, it looks like it's stored in memory right before the array. And when I accidentally index off the front end of my array, I can see it. I do the same thing in the other direction. I look at element 3, which is off the end of the array, and element 4 even more so. And I get a 25 and what looks like garbage. I bet that 25 is the storage for my variable x. Again, the standard doesn't guarantee that, but it looks like my compiler put that x right after the array in memory. So whenever you access on the array, off the end of an array, you're really looking around or accessing other parts of your program's memory, potentially changing other variables. This is kind of what we saw in the sample program. X and Y are stored, and apparently in this example, right before and after that array. We'll talk about this a little bit more later, but you're really looking at how the compiler is storing the local variables used by a function. Some people would say this is the stack frame for that function. Every time you call a function, it has to allocate a little bit of stack space for its local variables. the structure of that space, how those variables are organized in memory. Some people would call that a stack frame. It would contain those variables along with other stuff. So it's kind of like we're peeking around at what's in that stack frame when we, well, I would say accidentally, although backing up here, I did it on purpose, when we're looking off the end of that array. It's kind of fun in a sample program like this, but this would be an error in a real program, especially if you went off the end of the array and modified memory that's there. Like I started to say a moment ago, this is one of the most common reasons for programs crashing when they run in C, is if you make an array and then you accidentally index off the end of the array in either direction, an index that's too big or a negative index. So if during execution you see a message like segmentation fault or bus error, depending upon your system, and then your program terminates, that may be, this isn't the only thing that can cause that, but that may be because you accidentally went off the end of an array and maybe overwrote some memory that you were using to store something else. These kinds of errors, accessing memory that you're not supposed to, and especially modifying that memory, these can be tricky to debug, because if you overwrite something by accident, it's probably going to crash your program, just probably not right away. If you accidentally overwrite one of your variables with something else, it might crash your program later when you actually go use that variable. And that's tricky to debug, because when the error shows up, when it crashes your program, maybe the thing you did wrong happened a while ago. And it's a little hard to go back and figure out what eventually caused your program to crash. We will see some tools a little bit later that can help on that. But just until we see those, well, even when we do, the programmer still has to think about this kind of thing themselves to avoid these errors, and just try to be extra careful with array bounds use, because you don't have a runtime environment that's checking every array index for you, at least not in C. This can be a big potential security hole. If every array indexing out of bounds on an array could let you access nearby storage within your program, who knows what's nearby in memory? Here, it's a silly picture I made, but it's showing, pretend you've got an array. Well, other stuff around that might let you accidentally modify variables in your program. It might accidentally let malicious code see or change parts of your program that you didn't plan on it seeing or changing. So any potential out of bounds access in an array could crash your program or could be a vulnerability. One that's particularly common, or an exploit that's particularly common, is usually described as buffer overflow. And that's what happens when I'm reading input, either from a human user or from another program or something like that. And if I don't do bounds checking myself, let's talk about this example at the bottom. So here I prompt the user for some numbers. I make an array where I'm going to hold up to 20 numbers. And then I just keep reading numbers from the user. I call scanf, I read an integer, I put it right in the ith element of the array. Notice I put an ampersand in front so that I'd be passing the ith element by reference so scanf can change it. And then after I successfully read a value, I increment I, and then I try to read into the next element of the array. If a malicious user just kept entering values, if they entered more than 20, then they would trick this program into writing past the end of this list array, potentially writing somewhere else. So if you ever give another user or a program the ability to trick your program into writing past the end of an array, then we would call that a buffer overflow. And it's usually the kind of thing that an attacker could exploit. I've said this a couple of times, but I'll say it again real fast. In Java, it's harder to make this mistake because every access to an array is bounds checked. But in C, this is up to the programmer. You need to think about whether or not a malicious user could trick your program into accessing memory past the end of an array. Well, this is something that's harder to exploit now, but it used to be a pretty common trick to exploit buffer overflows by writing not just data into your program's memory, but actually writing executable code into your program's memory. An attacker could trick your program, well, could write machine executable instructions into a buffer. And if they overflowed the buffer enough, they could actually write into part of your stack frame the address of the code they just wrote. So that when the function that had that error returned, when it was done running, and it tried to return back to where it was, instead, they could trick it into returning to not back where it was, but when it tried to return, they could trick it into jumping into this evil code that they wrote and getting your program to do something it shouldn't. This is harder to exploit now because of the way memory is accessed in hardware. They kind of, with help of hardware, we can make this harder to take advantage of. But there are still plenty of things people can take advantage of by tricking existing utilities into writing malicious code into their own memory. And if you can inject just a little bit of malicious code, and that's what this is showing down at the bottom, a standard sequence of instructions that you could trick a program into executing. You can use that to trick it into executing just about anything you want. We've got a class that you could optionally take later, CSC 405, if you want to see more about this kind of thing. And coming from the C class and the assembly class, you're set up well to understand what happens in a lot of these exploits down close to the hardware level. Questions before we try to move on? All right, we learned about arrays. We learned how to declare them. We learned how to access their elements. We learned how to initialize them. We learned this bounds checking stuff. What else can you do with an array? There's very little syntax in C that works with the whole array at once. And remember that, because this is a common mistake for people to make on and on into the semester. I've got it here on this line. Let's say you had two arrays, list one and list two, and you wanted to copy one list to another. You can't do that in C. You can't really do it in Java either, not with just an assignment like that. And that's some of what I'm saying. There's not a whole lot of syntax that works with a whole array at once. You could copy individual elements out of an array, but you can't copy from one array to another just by assignment. There is one little bit of syntax that works with a whole array, and that's size of. We talked about this, I think last time or the lecture before that. Remember, size of is a built-in operator, and it tells you how many bytes it takes to store a thing. And if you give size of an array, it will compute the number of bytes it takes to store that array. I'll go ahead and warn you, we'll talk more about this later, but this only works in the scope of the array's declaration. We'll see if you pass an array to a function, this won't work, so be careful about that. I think I've got a whole slide for that later. But if you declare an array, like if you're in main, and if you declare an array and then later on you ask size of that array, as long as you're in the scope of that array's original declaration, then you can ask size of on the array, and that'll tell you how many bytes it takes to store that array. But like I said, other than things like that, there's not a whole lot of syntax that works on a whole array at once. You can't assign between arrays. You can't concatenate arrays without writing your own code to do that. If you want to copy from one array to another, or you want to do some other operation on an array, then usually that'll mean you're going to write a loop to do that. And that's just a little bit of extra code. Here, if I have an array source and I want to copy it to a destination, and I know how big the destination needs to be, it's easy enough just to loop over all the array elements, copying them over one at a time, one after another. Backing up a slide, you can't do this to copy the array. But if you're willing to go through each element, you can copy each element from a source to a destination array. I mentioned this already. When you make an array that's a global, or in general, when it's statically allocated, so that'd be a global or a static local variable, its size has to be constant, has to be a constant expression. So the compiler's got to be able to plan for how big that array is, and it has to know that when it's compiling your code. But this isn't true with local variables. In C99, they made it, and so this has been around for a while, they made it so that you can have what are called variable sized or variable length arrays. And that's where the size of the array is determined by a variable, or in general, an expression. And here's an example of doing that. I declare a variable n. I don't set it to anything, I get it from the user. So I ask the user, how many values do you want to give me? They hopefully type in a number, and I store that in my variable n, and then I make an array that's that big. So the size of this array is determined by some, so let me first say this works. It'll allocate an array where the size is determined by how much or whatever the user entered here. Here I didn't put any error checking code in. This will compile and run just fine, but it's worth thinking about what happens if the user entered 0 as the size of an array, or what if they entered a negative value as the size of an array. This will compile just fine and it'll run, but the behavior might not be what you want, especially if they enter a negative value for that. Variable sized arrays can be any size they need to be, as long as you have enough memory to store that, but you can't change the size of that array after you've already made it. And here's an example of what I mean by that. Here I do the same trick. I get a input value from the user for how big the array is. I make an array that's that big, and then let's say I do some stuff with that array, and then I want to change my mind about its size. I read another value from the user, and now I try to make list that size, make it some different value of n. This won't work. Well, partly because you can't change the size of the array once you make it. And also because for the compiler, this is going to look like you just want to make two different variables with the same name. It'll say, well, you already got a list up here. You can't make another variable in the same scope that has the same name, even if you're trying to make it a different size. So this won't work for variable length arrays. You can make them any size you want, but you can't change their size once you make them. But you can do this. Here I've got a loop, and every time I run the loop for 10 iterations, and every time around, I ask the user for a different value of n, and then I make a variable that's that big, that has that many elements, and this works just fine. Because every time around this loop, this variable list is going out of scope. And then when it comes back into scope, when I make it again, it could potentially be a different size. That's fine. Every iteration of this for loop can have an array that's a different size. You can't change the size of the array once you've made it. Here, I'm technically making a new array on each iteration of the loop. Questions?
So this wouldn't work if you had an array as like a macro or something?
Say that again. If you had an array of,
like you declared it at the beginning of your program, and you said like, I want an array that's like this size, and then you change it.
If it was a global, yeah.
Yeah.
So if you put it outside any function, you can't do this trick. Maybe it's not clear how you would even try to do this trick, because if you're trying to read from the user how big the array is, how do you get that variable into the array declaration? But either way, it doesn't matter, because in C, global variables have to be statically sized. We'll learn some tricks to get around that later, but for now, using what we know, they have to be fixed size. They have to be compile time constant size. Other questions? All right, I mentioned size of and how it works on the whole array. It computes the number of bytes to store all the elements in the array. And again, I gave you a warning that says, if you pass an array to a function, size of can't really tell you how big it is. It only works when you're in the scope of the array's original declaration. And later, I'll say this one more time, and then I'll try and stop saying it. Later, I'll explain, here's why that's going wrong. But here, no problem. I declare some variables up here, and then I ask how big they are. And here, remember, this is kind of practice on the sizes of the primitive types on the common platform, and it's worth it to just know that an int is 4 bytes, that a float is 4 bytes, that a double is 8 bytes. I would memorize that for all of the primitive types on the common platform. There aren't too many of them. All right, knowing that, I make an int a, and then I ask, how big is that int a? Well, like I just said, an int is 4 bytes. So size of a is going to tell me 4. Well, I make an array B of 100 floats. I just said a float is 4 bytes also. So 100 floats is going to be 400 bytes. So if you ask the size of B, it should evaluate 400. You can see here I'm storing it in a variable, and I'm using this size t that we talked about a couple of lectures ago. That's the type for the sizes of things. And then at the end, I make an array C with space for 16 doubles. Each of those is 8 bytes in size, so that should add up to 128 bytes for array C. Here, I'm going from, we're kind of looking at how big these arrays are, how many elements they are, and using that to figure out how many bytes that must take in memory. You can go backward from this, and this can be awfully useful to figure out the size of an array, or I guess said better, to figure out the number of elements the array has. This only works if the compiler can figure out the number of bytes it takes to store that array. And I've given you a couple of warnings that if you pass the array to a function, it can't do that. But if you're in the scope of the array's declaration, this works just fine. So here I make an array B with space for 100 floats. And then down here, I want to figure out how big the array is. So I take the size of the whole array divided by the size of just one of its elements. I could have said float here, and that would have worked fine. But instead, I just ask the size of element 0 of the array. And I guess the nice thing about that is if I went up and changed my mind about the type for this array, if I changed it to double or int, then this would still work because I'm asking how big's the whole array divided by how big is just one of its elements. And this will compute the number of elements in the array, like it says in bold down here, not if you pass the array to a function, but if you're in the scope of the array's declaration, this is a handy way to figure out the number of elements. Do you really have to figure this out? It says 100 right there. But I guess I would say this is good for code maintenance. If you went and changed the size of the array and you said, oh, now I need it to be 200 elements, this code will still work just fine. As you change the number of elements in the array, this will correctly reflect how big it is. Size of, even though we're calling it kind of like a function, remember it's an operator in the language. And a lot of times the compiler can figure out size of at compile time. So for instance, if it looked at this variable declaration, it says, oh, I see you want a 100 element array. Every float is 4 bytes. So this is 400. So that's 400 divided by 4. It can figure all that out at compile time. And in this case, this would qualify as a constant expression. This is something the compiler can figure out. All right, that's single dimensional arrays. I want to start talking about multi-dimensional arrays. Questions before we go on? All right. How do you make multi-dimensional arrays? Well, if the size of a one-dimensional array comes after the name, the same goes for all the dimensions. Here, I'm making a two-dimensional array. I called it table. And you wouldn't have to think of it this way, but it's common to think of the first index as rows and the second index or the second dimension as columns. So I'm making a table with 3 rows and 4 columns, a 3 by 4 two-dimensional array. If you make an array like this, the way you get its elements is just like you would in Java. You stack up indices after the name of the array. So in my top example there, I'm asking for table at row 2, column 3. And both of those work just like you'd expect. If I've got 3 rows in the array, then I've got a row number 0, 1, and 2. If I've got 4 columns, then I can have column numbers 0, 1, 2, and 3. That's 3 different columns just ranging from 0 up to but not including 4. So you use 2 indices to get an element out of the array. You use 2 indices to put an element in the array. When you make an array like this, you normally think of it, I drew a little picture up there in the corner to show how we normally think of this. We think of it as rows and columns. A multidimensional array in C is really just an array of arrays. So if you want to initialize it, you just have to give an array, you have to give a sequence of initialization values for each element. So if table is an array of an array, sorry, if it's an array of arrays, then it's a 3-element array of rows, where each row is a little 4-element array. So to initialize it, I just need to give the value for each row, comma separated, just like I would for a 1-dimensional array. But each of those values is itself a little 1-dimensional array. So every row is 4 elements. I just write out each of those 4 elements, comma separated, inside curly brackets. Since table is 3 of those rows, like I said a moment ago, I just put the initialization expression for each row, one after another, separated by commas. And then at the bottom, I'm just going through it and printing out each of the elements in the array. Partial initialization works just fine for multi-dimensional arrays. It's a little more fun here because you can leave out elements within a row, like I'm doing on that top row. The top row should have 4 elements, but I only gave 2. So the remaining elements in that row are going to get initialized to 0. The next row, I initialized the whole thing. The last row, I left out, I just gave the first element. So the remaining 3 elements will be initialized to 0. I don't have an example of this, but I could have left out an entire row. If I didn't have this 64 inside curly brackets at all, then this bottom row would be full of zeros. So you can leave out elements within a row or leave out whole rows. In fact, if you mix this with the C99 syntax, you can jump all over the place in the array. So the C99 syntax would let you say the index of an element within a row, or it'll let you say the index of an entire row. And that's what I'm doing at the start here. I want a 3 by 4 table. Let me tell you about row number 1. So this sequence, 1625, 36, 49, goes at row 1, so that fills in this row. And then after I've done that, I back up and say, oh, now let me tell you about row 0. And then within that row, I skip around. Effectively, I'm saying, I don't want to talk about element 0. I want to talk about element 1. Just put a 1 there. So that's where this 1 comes from. That's the only thing I said about row 0. So the rest of these elements get initialized to 0. You can even give multiple indices if you want. So I jumped down and said, well, row 2, element 0, I want that to have 64. And then I didn't say anything else about that row, so all of its elements are going to be 0. So you can use this to, especially if you had an array that was mostly sparse or where you wanted zeros in most places, this syntax could let you jump around and specify, put this here, and anything I didn't mention, just leave it at 0. Questions? All right, I mentioned this before. I said when you're specifying an array, you can let the compiler figure out the size of that array. And that's what I'm doing on this slide. Here I made an array A, and I said, I'll just figure out how many rows it has, but it's going to have 3 columns. Here, for every row I gave 3 elements, I gave 2 rows, so the compiler is going to figure out, oh, you wanted a 2-row array where every row has 3 elements. And the compiler will let you do that just fine, but it won't let you leave out anything except the first index. I think of that as the outer index for the array. Even if you're consistent on it, here I've got the same initialization expression. You and I can tell, well, this is an array where it looks like you want 3 elements in each row and you want 2 rows, but the compiler won't let you specify it like this. In general, the compiler is very uptight about all the dimensions except the outermost one. And again, when I say outermost, I mean this first index into the array. The inner dimensions, you generally have to specify. They can still be variable sized, but the compiler doesn't want that unspecified. And the reason for that is because of how the compiler is going to build this array. This is how arrays are built in C. At least this is the standard way that multi-dimensional arrays are built. And it's kind of one reason arrays can be really efficient in C. An array in C is an array of arrays. So that means a 2-dimensional array like this, if you think of it as being an array of rows, then the way the array is stored is one row after another in memory. So this top picture shows how we might think of that array, but the bottom picture shows how it's really stored. The first thing in the array, well, that's the first row. And that first row is an array, so it's just elements one after another in memory. And then after the first array, after the first row, is the second row, one after another in memory. And then the third row, one after another in memory. And I may have said this a moment ago, this is called row major order. And as long as every row is exactly the same length, then even if it's laid out like this, as long as I know where the array starts in memory and I know how big each row is, we can figure out where to go in memory to find a particular element. And we'll talk more about that later. But because of this, to look up an element in the array, the compiler needs to know that all the rows are the same length for this trick to work. And it needs to know how big each row is. Because if you ask me to look up something in, let's say, the bottom row here, well, I got to skip past the first 2 rows before I can even start looking in the bottom row. But as long as every row is exactly the same number of elements and every element is exactly the same size, doing that just requires math. But because the length of every row is needed to index into the array, the compiler, backing up a slide, it really wants to see the width of this array as part of the declaration. So that's why it's so uptight about that. And we'll see some more examples of that in a moment. If this is how C builds a multidimensional array, this is more like how Java does it. In Java, an array is managed by a reference. So an array of arrays is an array of references to each of its rows. So a multidimensional array is kind of like what I'm showing in this picture. It's an array of references where each reference points to, refers to a little one-dimensional array in memory. There's some trade-offs with that, but one of the disadvantages of that is it can be a little less efficient to get stuff in that array. Like I said a slide ago, and really this is what I was talking about, as long as the compiler knows how big each element is, and it knows how many elements there are per row, and every row is exactly the same length, then moving from column to column, let's say this is an array that's a 2-dimensional array of ints. On the common platform, an int is 4 bytes. So moving left or right, moving some number of columns is just a 4-byte move for each column. Moving up and down, well, every row has 4 integers. Every integer is 4 bytes. So moving down a row is just 16 bytes. Moving down 2 rows is 32 bytes. So the compiler can efficiently, or can write code to efficiently look up stuff in the array, as long as it's guaranteed that every row of the array is a particular length, and it needs to know that length. But it doesn't actually need to know how many rows there are in the array. To look up an element, it just needs to know how big each element is and how many elements there are in each row. It doesn't actually need to know how many rows there are. If it was going to do bounds checking, it would need to know that, but we already said C doesn't do bounds checking for us. So it doesn't actually need to know the size of the outermost index to look up stuff in an array. And we'll talk, I've got some slides later. I was hoping these were my next slides, but we'll see that when we start passing arrays to functions. In an array, you can specify one or more indices to take the array apart, kind of like you would in Java. And an easy way to see this is when you're using size of. Here, I make a table. It's the same size we've been playing with. I make a two-dimensional array of ints with 3 rows and 4 columns. And if I ask size of on the whole table, well, it's got 3 rows. Every row is 4 elements, and every element is an integer. So that's 3 times 4 elements per row, 3 times 4, times 4 bytes per element. So 3 times 4 times 4, 4 times 4 is 16, 3 times that should be 48. So here I should get 48 bytes for the size of the whole table. If I just stick one index on it, then I'm asking the size of just the first row. And you can do that. You can, just like in Java, if you just put one index, you're asking about, well, one element of this two-dimensional array. And in that case, one element of the two-dimensional array is a row of the array. So here, if you ask size of row 0, well, row 0 is 4 elements. Each element is 4 bytes in size, so this should tell you 16. If you look up just the element in the upper left corner, the element row 0 and then column 0, that's just a 4-byte int. So you can use size of, and in general, you can take apart an array, an index at a time. This lets you talk about the whole array. This lets you talk about just one of its rows. This lets you talk about just one of its elements. Questions? So here, I would say, kind of like it says at the top of my slide, we're seeing evidence of how this is stored as an array of arrays. So it's a three-dimensional, sorry, it's a 3-element array of 4-element arrays of ints. Sorry, I interrupted someone. Someone was asking or saying something?
Yeah, the size of the table 0, 0 means that's accessing the element on that like table, and like a 0 row and 0 column.
Yes. So here, maybe I should have picked something with different indices here, but table row 0, column 0, well, it's a 2-dimensional array, so that's just one element. Every element is an int, so that would be 4 bytes if you're asking size of.
Professor,
Yep.
what's going to be the size of the table 0 again? I didn't get that.
Oh, here? Table 0, so here, if you just give the first index, you're asking about one row of that table. Well, every row has 4 elements. So, and every element is an int, so that should be 4 elements times 4 bytes per int. So that middle one should be 16 bytes.
Oh, okay, thanks.
Professor, I'm still not clear for the the last one, 0, 0. That's the the memory of that element, or the actual that element?
Oh, since you're saying size of, notice all of these have size of in front. So if you didn't have this size of here, then you're using that element. You could put something in it with assignment, you could get something out of it. But if you stick the word size of in front, if you use the size of operator, you're not asking, you're not trying to change what's in that element. You're just asking the compiler how much memory does it take.
Okay.
So here, yeah, it's kind of like you're looking up the element at row 0, column 0, but then you're asking how big that is. So you're not even really using the element. You're just asking how big it is. And that would say 4 bytes in this case, or it would evaluate to 4. I mentioned arrays can be allocated statically or they can be allocated on the stack. And this gives us a new mistake that would have been hard to make earlier. And that is the potential of running out of stack space. Depending upon your execution environment, stack space could be limited. Well, how could you run out of stack space? If you made a recursive function, every time you call that function, it needs a little bit more stack space. So if you called a recursive function very, very deeply, you could use up your stack space. But otherwise, it's hard to have a function that declares so many variables that it uses up a whole lot of stack space. But that's easy to do with an array. Here, if you make a small array on the stack, no problem. 10 elements of size int, that's easily going to fit on the stack. But if I go down and say I want, I don't know how many zeros there are. Let's say that's 10 million, 1, 2, 3, 4, 5, 6, 100 million ints worth of storage. That's probably not going to fit on my stack. And when I call this function and I start trying to use that table, it's probably going to crash my program. This is, I guess, our first easy way to run out of stack space by making an array that's too big. What if you need an array that's really big like this? Well, for now, you'll just have to store it somewhere else. The static region of memory does not have this kind of limitation. So as long as the function didn't need to be called recursively, you could maybe get away with just one array that was that big and just use it inside the function. So here I moved it into I made a global variable instead, and this should work just fine as long as you only need one table like this. Later, we'll learn another way of doing this. We'll learn, I mentioned heap memory. We'll learn how to use that ourselves, and that also would let us store a table that's bigger than we could store on the stack. All right, what does it take to pass an array to a function? Well, if you want to define a function, so you've got an array, you want to pass it to a function as a parameter. When you pass the array to a function, you just have to say its size, just like you were declaring the array. So here I made a function report that's expecting an 8-element array of integers. Here I made another version of report that's expecting a 5 by 8 two-dimensional array of integers. So you can specify the size of the array explicitly when you declare the function. And that's probably the easiest way to think about doing it. But like we said before, the compiler doesn't care so much about the outer index. It cares a lot about how many elements there are in this two-dimensional example. It cares a lot about how many elements there are in each row, but it doesn't really care how many rows there are, especially if it doesn't have to allocate space for that array. Here's an example showing this off. I made 3 tables. One is 5 by 8, exactly like the function is expecting. One of them is a little bit taller, 6 by 8, and one of them is same height, but a little bit wider. The compiler is just fine with me passing a 5 by 8 array to a function that's expecting a 5 by 8 array. It's also perfectly happy with me passing a 6 by 8 array to that function, even though it's taller than what the function is expecting. But it won't let me pass a 5 by 9 array, an array that's wider but the same height. And the reason is what we already said before. As far as that function is concerned, since it doesn't have to make the array, you're just giving it an array that you've already got, it doesn't really care about the outermost dimension. Let's talk in terms of two-dimensional arrays, because that's easier to talk about. If this, backing up, if this function is expecting a 5 by 8 array, it could work fine with a whatever by 8 array. Indexing into its elements, all I need to know is how wide is every row, And how big is every element in that row? I don't really need to know how tall the array is in order to index into it. Like I said before, I would need that if I was doing bounds checking, but C doesn't do bounds checking. So passing an array to a function is really more like what I'm showing here. In fact, this is how most people would code it, and this compiles just fine. When you pass a two-dimensional array to a function, the compiler will let you just leave out the first dimension because it doesn't care about it anyway. It doesn't need it to do bounds checking because it's not going to do that, and it doesn't need it to index into the array. So for a two-dimensional array, you'd probably pass them like this, or at least here's how you'd write it. It's fine if you put a number here, but the compiler's just going to ignore it. For a one-dimensional array, you can use this syntax. Well, here it's only got one dimension, so you can leave that unspecified, and this function would take, you could think of it as taking an array of floats of any length. Here for a three-dimensional array, well, I said it doesn't need to know the outermost dimension, but it needs to know all remaining dimensions because it's going to use that to look up elements. So this works fine in passing an array to a function. I said this a couple of times already, but here we've got an example of it. This does not work in a function. Remember, we learned that trick before of computing the size of an array and dividing it by the size of one of its elements to figure out how many elements are in the array. Now that doesn't work when you pass an array to a function. That's why I put this big, this doesn't work star here. Because the function doesn't actually know, for a one-dimensional array, it doesn't actually know how many elements are in that array. For backing up for a two-dimensional array like this one, it doesn't actually learn, it's not actually told how many rows are in the table, just how wide each row is. It has to know that, but it doesn't actually care how many rows there are. And since it doesn't know how big the array is, it can't figure it out just by asking size of on this. An irritating thing about this is this will compile just fine. You might get a warning from the compiler. This means something. It just doesn't mean what you probably want it to mean. So be careful about this. You might want to try out the compiler and see if it gives you a warning on this. I feel like I've seen compilers give warnings on this, but I haven't checked recently about this. So if a function doesn't know how many elements are in an array or in a two-dimensional array, if it doesn't know how many rows are in that array, how does it find out? Usually you got to help it. If you want to make a function and you want to give it an array of ints, and you want it to look at every int in that array, you're probably going to have to also pass in a parameter that says how many elements there are. So this would, here I'm passing, my plan is I'm passing, here's how big this array is, and here's the array. And then the function can, I tell it how many elements are there. So this would let it know how many elements are in the array. Same for a two-dimensional array. This function expects a table of who knows how many rows, each of them 7 elements wide. I told it how many rows there are, but I had to spend an extra parameter to do that. Well, we talked about strings, and we'll see soon strings are really just arrays of characters. That's one special case where you usually don't have to tell a function how long the string is, because we already said we usually depend on having an end marker for the string. The null terminator at the end of the string, usually we can depend on that to tell a function how many characters are in the string. So that's one special case where we don't have to do this trick. But if you're passing a function, passing an array to a function, you should think about, well, do I need to tell the function how many elements are in the array? Backing up, because this doesn't work. Java has the dot length that works on an array. And this is kind of like that. It just doesn't work in the case where you'd probably want to use it most, and that is if you pass an array to a function. Questions?
Yeah. A little while back, you said something about it can ignore the row number whenever you're doing a two-dimensional array.
I'm not sure that's what I said, but Here, I said, when you pass a two-dimensional array to a function, you can leave out the number of rows because the function doesn't need to know that to index into the array. But
So if you did like
realistically, what I'm saying here is, yeah, but if you're gonna look at every row, someone's got to pass you the number of rows, or you know, probably you're gonna need to know that.
So if you're going to do an assignment to like a row that, if you give it like a row number, like say 6 and 12 as the two-dimensional parameters, and you assign something to like 7, 12, would it still be like an overflow?
I didn't completely understand your question, but I'm going to say yes, it would be like an overflow. Hang around after class and I can give that a little bit more attention.
Okay.
Yeah, I apologize for shortchanging your question right now. I just want to get through this topic, which is variable sized arrays. Remember, we said you could make arrays where the dimensions are not constants or aren't known at compile time, and you can even pass arrays like that to a function. It's just that the type of the array is going to include the variable size. So if I want to pass a table that has, well, I can already say who knows how many rows, but I have to say the number of columns. But what if that isn't known until runtime? What if I read that from the input or something? Well, you can do that. You can put a variable here as the width of the array. It just has to be a variable that's already in scope, which you can do if you pass it in as an earlier parameter. So here I'm calling a function. I'm saying I'm giving you a table. Here's how many rows there are. Here's how many of the columns there are. And since these two variables are earlier in the parameter list, it's okay to do this, to say, oh yeah, the table is, you know, that columns I just passed you, that's how wide it is. So you could call this function multiple times with tables of different sizes, different widths, different heights. And as long as you told it how big how many rows and columns it has, and you didn't lie about that, then it would work just fine. So here's how you can pass a variable sized two-dimensional array to a function. Like I said a moment ago, we're counting on the caller telling us the truth in this. Here I make a 10 by 12 table. I got a function that's expecting a table of any size. If I call the function and I tell it the truth, it's going to work just fine. But there's nothing to keep me from lying to the function. If I say, yeah, that table's 20 rows and 13 columns, this will work. It'll call the function, but probably I'm not going to get the behavior I want out of the function because it thinks it's got a table that's 13 elements wide, but I really made a table that's 12 elements wide. So this counts on the caller playing fair with the function. We already said this a little bit, but I'll try and make it clear. Since when you pass an array to a function, the function isn't getting a copy of the array. Just like in Java, it's getting a reference to an array that the caller better already have. That means that you get reference semantics when you pass an array to a function, just like you do in Java. Here's a picture that shows how you can think of this. I make a table, I call a function and I give it my table. Inside the function, I'm accessing the table. The function doesn't get a copy of the whole table. This is why the size of trick doesn't work, because its table is really just a reference to the table that someone else already made. But it means that in the function, if you change what's in the array, you're really changing the caller's array. So the caller, whoever called the function, made a table, made a two-dimensional array. We gave it to the function. If the function goes in and starts modifying its elements, well, it's modifying the same array that the caller created. So it means that when we return from this function, we can see changes to the contents of that array. One detail, when you return from functions can take array parameters, but they can't really return arrays as return values. I guess in C, if I had to try to write a function that returned an array, this is the syntax I would use. The size of the array that gets returned would have to be out here. after the function name, but it doesn't matter because this doesn't work anyway. You can't return an array from a function. If you want a function that puts something in an array, well, you could, in an array, you could pass the array to the function, and then the function could fill it in. Questions? We got one more topic. We got 5 more minutes. We'll see if we can make it. 4 minutes now. All right, I said this already. One important thing we do with arrays is we use them to store strings. In fact, that's how strings are stored in C. They are arrays of characters. Not every array of characters has to be a string. You could make an array of characters that isn't a string. It's just a sequence of characters. That's what I'm doing here up at the top. I make an array A of characters. I put 6 characters in it. And then, well, I say exactly what each character should look like. You get a sequence of 6 elements, one after another, initialized to whatever you specified. And if you ask the compiler size of on that array, it's going to say 6 because you made 6 elements. They're each 1 byte in size. So this is what you get in memory. But I wouldn't call that a string. It's just a sequence of characters in memory. Because remember, in C, we use this trick of marking the end of every legal string. And that's so common that there's a shorthand syntax for doing this. It's even easier than what we were doing earlier on the slide. If you make an array S and you initialize it with a string inside double quotes, it's going to build this array. It's going to initialize it with 7 elements, the 6 that you explicitly said, and 1 extra null terminator at the end. Just if you looked at the byte there, it would just have the value of 0. So initialized like this, you'll get a real string. And like I said, you can see this if you ask size of. If you say, how big is this array? It's going to say, well, it's 7 bytes. The 6 characters you asked for, plus that 1 extra end marker. Questions? Remember, for long strings, you can just space separate them. And this, again, this would make sense for a string that was so long you didn't want to put it on 1 line of code. This also works when you're initializing an array to hold a string. So this works just fine. All these are going to get glued together into 1 big string. And if you asked size of, well, all those characters inside the double quotes add up to 15 characters plus 1 more for the null terminator. So this guy would be 16 bytes long. This trick for concatenating strings, that only works for literal strings. That's kind of a compile time trick. It's not a general purpose string concatenation operation. So you can't just put 2 strings one after another and expect it to concatenate them. That only works when you're writing 1 big literal string. We'll learn how to concatenate strings. It'll be a little trickier than I'd like it to be, but it's not as easy as just putting 1 string after another. Well, we learned how to use printf for printing out strings. We just didn't know how to store string in a variable, so it was hard to use that for much. You'll remember %s is for printing strings. It works on literal strings, but any string stored in an array, you can also print that with %s. So here I make an array that contains, well, there's a typo there, it should be CSC 230. And then I try to print that out. This will print fine with %s. In general, %s is expecting a null terminated string, and that's what I get here. Backing up a couple of slides, if I tried that on A up here, well, I deliberately made it so it's not a null terminated string. And if I tried to print it with %s, I'd probably get all these characters plus some garbage at the end. Because if I didn't really put a null terminator there, then printf isn't going to know for sure where that string ends. And here's our last slide. The same thing goes for reading strings. You'll remember %s also reads a string, where a string is, you can think of it as a word. It skips white space, and then it reads the next contiguous sequence of non-white space characters, some letters, numbers, until it either hits the end of file or hits more white space. So that's kind of like reading a word or a token. This will read it and store it in a string for you. So if you make an array word and then try to read with scanf %s into that, it'll store it in this array. A couple of things to notice. I didn't put an ampersand in front of the word. And the reason is we just saw arrays are automatically passed by reference. So I don't need anything extra to pass them by reference to scanf. It can already change what's in my array, so you don't need the ampersand here. This word is a 30-element array of characters. Since every string has to have a null terminator, you can think, and you should think of that as room for a 29-character string, because every string's got to have room for that end marker. So this, even though it's a 30-element array, it's room for 29 characters and the null terminator to mark the end. And one more thing, buffer overflow, like we talked about before. What if you ran this and the user typed in a really, really long string, longer than 30 characters? Well, here, scanf doesn't know how big your array is. It's just going to keep reading characters into that array, including off the end of the array. So this could easily trick scanf into buffer overflowing. So I'd say this is bad code. We'll figure out how to fix it, but it'll be a couple of lectures before we do that. I've overspent my time a little bit, but we did get through all of our material today. So we'll end lecture here, but I'll hang around if people have questions. Let me go ahead and stop the recording.
Yeah.